Welcome to Intelligent Systems, an introduction to artificial intelligence. In this video, we will look into how to represent and search text as a vector. We will start off doing the same for images, and we'll find that we can use different distance measures, Euclidean distance or the angle between vectors, and we will introduce the K-nearest neighbor algorithm to efficiently search for the nearest neighbors in the vector space. We then apply something similar to text, and first of all we need to represent the text as vector, and to do so we will introduce the tfidf model, the term frequency inverse document frequency, a workhorse and natural language processing in which we count words and normalize that by how often these words appear across all of the documents. We will then see that tfidf, while very, very useful, is not really capturing meaning, and then we finish the lecture by looking into the recent developments of the word2vec model and then the BERT transformer model, which underlie ChatGPT, that address this problem of capturing the meaning of words. Representing an image as a vector is fairly easy. We just turn the matrix, in the case of MNIST 2 by 28 by 28 pixels, into a vector, in the case of MNIST of 784 dimensions. Once we have the image present as vector, we can compare vectors in terms of some kind of similarity or distance, and an obvious candidate is the Euclidean distance, and this can be defined as the square root over the sum of the different dimensions subtracted from each other. So W minus V for two vectors V and W, and we take the Euclidean norm of the subtraction. And the Euclidean distance ranges from 0 for identical vectors to infinite in the worst case. Now let's apply this to a search. And in Euclidean space, the most similar vector for this image is that image over here. And that means out of all of the 60,000 training data images in MNIST, that picture over here is the most similar, and as you can see, it is very similar. Now we can turn this checking of similarities into a prediction task by simply saying this was from the training data and was labeled. This is query data unlabeled. So simply pick the closest and make the label of the closest the prediction of the query. So in this case, that is a 1. So our prediction is the query is a 1. And the algorithm that does this is called KNN, K-nearest neighbors. And very often it's approximated, and then you see it as ANN, approximate nearest neighbors. And there are libraries, because this search for the most similar vectors is very important for all kinds of data, for audio, for text, for images, and that's why Spotify, Facebook, and Google have invested. And 3 frequently used libraries exist: Annoy, Face, and Scan, by these large companies. So let's look into how Annoy works. It has a funny name, approximate nearest neighbors, oh yeah. And these libraries, they pursue different algorithms to achieve the same. And what Annoy does, it introduces random hyperplanes and creates a hierarchical kind of binary tree search in order to find the nearest neighbors. So it proceeds in 2 steps. In the first step, the tree is constructed. So the data is iteratively split along a random hyperplane, and that means for each data point you can determine whether it's above or below the plane and create this division. And you do this for multiple such planes, and that way you have basically a binary tree structure where the leaves are small subsets of points. And then during search, you use this tree structure that you created once for querying by traversing multiple trees, to find the approximate nearest neighbors of your given points. And the advantage is that you can balance accuracy versus speed. The more trees you have, the higher the accuracy is, but of course also the slower the query time. And if you have fewer trees, this is exactly opposite. So the library is really very easy to use, and with a handful lines of code, you can index the 60,000 training images of the MNIST datasets, and querying up to 10,000 also takes less than a minute. So very useful piece of software. So if we implement this K-nearest neighbors with the Annoy library on MNIST, then we're actually doing fairly well. Just as a reminder, classifying MNIST images randomly would have been 10% because our training data was equally balanced between the digits. And then we did a very simple approach, which is already a one nearest neighbor approach. That's what we implemented in the very beginning, where we took the shortest Euclidean distance to a random template. That is, for the 0 we got a template, for the 1 we got a template, 2 and so on. So we had 10 templates. So that meant we only did 10 comparisons for our query image and picked the template that has the best Euclidean distance. And that gave us 25%. So we were way better than random. And turned out that we got even much better if we averaged all of the templates, so the 6,000 zeros, the 6,000 ones we had, if we averaged all of these zeros, ones, twos, and so on, then this very, very simple algorithm got up to a success rate of about 80%. Then we implemented neural networks, and our first simple implementation, fully in Python, got us to 85%, but with TensorFlow and using convolution, softmax, and dropout, we brought it to 99%. Turns out that the super simple K-nearest neighbor approach is taking us here to 96%. Now let's look a little bit deeper into it. If we do Euclidean distance and we pick the first neighbor, that can take us to 95%. But the neural networks were better, and the question is, can K-nearest neighbors get better than 95%? And what we can vary is the K, and we can vary the distance measure. So what would it mean to vary the K? So instead of leaving K at 1 and picking the closest neighbor and making that our prediction, we could take the top 5 K neighbors, the top 10 closest neighbors. And then we could look at those 5 or 10 labels and make up our mind what the best prediction is. And in terms of distance measure, instead of the Euclidean distance, we could, for example, measure the angle and implement the cosine similarity instead of such an absolute value. Now, let's look why K-nearest neighbors might be useful. If we have this picture as a query, then turns out that among the 60,000 training examples, the most similar in Euclidean distance is this, which is clearer as 0, and that means we will get a wrong prediction. But if we look at the top 5, we get these pictures here, and you see that this, and this are all 6s, and that means 3 out of the 5 top predictions by Euclidean distance have the correct label, and so simple majority vote with K equals 5 will give us the correct result. And so varying K and not just sticking with the first one, but also exploring 3, 5, or 10 is a useful approach. However, it is also clear that as K gets larger and larger, it will deteriorate at some point. So take it to the extreme. If K was equal to 60,000, then of course the whole prediction task would become pointless. So at some point, there is a turning point in which increasing the K will substantially start to decrease the performance of the whole approach. Now, the other alternative was that we could change the distance measure. And why should we do that? Because Euclidean distance is not always the best measure to take. So here on the left and on the right, you see 2 images which look identical, but they're not identical because this image on the right is the left one with all pixels divided by 2. And the black is represented by 0, so that doesn't change. But here the white, this has become a little bit darker, although that's hardly visible on the screen as I have set it up. Now, modifying the pixel values and halving them means, in terms of Euclidean distance, that we introduce a pretty large distance. And since overall dimensions, this is added up, so that means for all of the dimensions where the pixels are gray or white, we will get a component that increases the Euclidean distance. Now, is there a measure in which this change in brightness does not have an impact on the distance measure? And the answer is yes, namely the cosine similarity. Because if we interpret the image as vectors, then halving all of the pixel values does not change the direction of the vector, it only changes the magnitude of the vector. And that means the angle of the vectors is 0. And this is captured by the cosine similarity, which is defined as the dot product of our two vectors, v and w, divided by the Euclidean norm multiplied with each other. So as a refresher, dot product we see here, that's the sum overall I of vi times wi. And the cosine similarity ranges from -1 to 1. -1 means the vectors are pointing in exactly opposite directions. 1 means they point to exactly the same direction, and 0 means they're perpendicular to each other. So what happens for this image case? Cosine similarity of both images is 1 because the angle between those two images is 0. Now, interestingly, despite changing the distance measure between Euclidean and cosine similarity, despite changing the k from 1 to 5 to 10, the overall success rate remains at 95–96%. The differences are really very, very small. That's quite interesting. And it turns out that a huge part of the images in MNIST is really very easy to classify, because in their direct vicinity, no matter whether you take Euclidean or cosine similarity, in their direct vicinity, they have images of the same label. However, at the same time, there are cases which are inherently difficult to classify. So overall, there are 157 images which, no matter which combination of parameters you use here and which distance measure you use, all of them get them wrong. And you see some examples of the 157 here. And the interesting bit is that to the human eye, they don't really pose such a huge problem. It's fairly clear that this is an 8, a 5, a 7, 5, 8. And you have to look hard. Maybe this one is difficult to classify for us, or here you could be unsure whether it's a 4 or a 9. But that's interesting. So only very few images get misclassified by all of the K-nearest neighbor approaches. And obviously, since the neural network approach was at 99%, it gets many of these right. And that is quite interesting. So the neural network, it's really dealing with a large part of the data that is very easy to classify, and all of those convolutional layers and so on, they really just kick in for a very small part of the images, where a deep understanding of the shapes over here, that maybe this is round, that there is a long vertical line and so on, where this really kicks in and makes a difference and brings it up to the 99%. So for images, we can define distance measure, and besides Euclidean and cosine similarity, there are of course also other measures that one can define. K-nearest neighbor search is available in many libraries and is very efficiently implemented, so that you can scale up to large data sets. Now, let's try to do the same for text. And let's just start with representing and searching text and not worrying about whether that's as a vector, because we do have an easy way to search text, and that is the Levenstein distance, which we got to know when we spoke about lexicon and matching text between a lexicon and a dictionary and some longer text, and we wanted to cater for typos and misspellings and so on. So the Levenshtein distance does the trick here, and it allows us to compare strings. However, at the time we discussed already that Levenshtein distance and its basic implementation has quadratic runtime, and that means if we really want to compute the similarity over huge amounts of text, over a massive database of spam ham messages, of email messages, or of social media posts and so on, then it's likely that Levenshtein is way too slow with its quadratic runtime. But the other thing is also that Levenshtein distance cannot capture the meaning of words. So if we take the two sentences, I need to buy a bike and I have to purchase a bicycle, then for the Levenshtein distance at the word level, a lot would be different. Only I, to, and a would be the same, but needn't have buy and purchase, bike and bicycle. They would be completely different, although the meaning of the two sentences is the same. So question is it possible to somehow address also similarity in meaning with a representation of text as a vector? Now, let's first of all address the problem of speed. And when we discussed Levenshtein distance earlier, we got already a solution. We spoke about decomposing strings into trigrams and letting go of the order of these trigrams and representing them as sets of, or string, representing a string as a set of trigrams, and then define a distance through, for example, the amount of shared trigrams or some normalized form of that. And let's do that here as well. And for the sake of simplicity, let's do that first of all, not for trigrams, but for words. And what we're taking into account here is the trade-off between speed, which we want, and information, because we drop the sequence information. So we gain through dropping that piece of information, we gain speed. So the string I need to buy a bike becomes the set a bike buy I need to. So the order has gone. And the same for I have to purchase a bicycle have I purchased too. Once we have represented a string as a set of words, we can make the next step and represent it as a vector, and that's fairly easy because we take the total vocabulary, that means we must really consider all of the messages, and we represent that as dimensions in a high dimensional vector. So we have now a bicycle, bike, buy, have, I need, purchase, two. So 2, 4, 6, 8, 9 dimensions. And now the sentence, I need to buy a bike, becomes the vector 1, 0, 1, 1, 0, 1, 1, 0, 1. And we can see some commonalities over here, and over here, and some differences. And that means we can now directly apply our cosine similarity, Euclidean similarity, and compare these two sentences. But as we said, we still do not capture the meaning of words. But before we consider that meaning of words, let's go on and see whether such a binary representation of text as a vector is really sufficient. So obviously it's not, because a sentence like I have to buy a bike and I have to buy a vase, we have multiple occurrences of I have to buy a, and that should be reflected in the vector. So by simply counting the terms, or the words, we can do so. So this sentence gets translated into 2, 0, 1, 2, 2, 2, 0, 0, 2, 1. And we call this term frequency when we're counting the words in our messages, and we don't leave it at binary. Now, we want to normalize that because we observed already earlier that words, trigrams, letters, all of these units of language, they do not have a uniform distribution in terms of their frequencies. But there are some words which appear very frequently and some words which are very rare. There's words like I to a, which commonly appear, and words like bike and vase and have and need and so on, that would be less frequent. And of course you can find extreme things like very specialized words that would be highly infrequent. So what we want to do is we do not want to give the same credit for a match or a mismatch or an appearance of a word that is very frequent and where it's hardly surprising that it's matching between messages, and one that is infrequent. So for example, the word the article, it's fairly likely that every message might be containing an So this should be offset. Whereas vase and bike, if vase appears, that is much more significant. So how do we represent this? By the concept of inverse document frequency. So that means we count for every word how frequent it is and in how many documents it appears that we have available. And a document in our case can be anything. It can be a short message, it can be a document on the web, a Wikipedia article, a paragraph, any form of context that we decide that we're looking into. And take these together, and that's really what you should memorize also as an abbreviation. tfidf, term frequency, inverse document frequency. That's the standard way how to represent text as vectors, and that is a representation that is widely used in natural language processing and when implementing search engines and so on. And let's just do that in an artificial way for our little example. Let's assume that we had 1,000 documents and I to appears really in all of the documents, buy, purchase, have to appears in 100, and bike and bicycle and vase appear only in 10. And with that, we can now represent our vectors with the TFDIs, with a tfidf score. And we have, for example, for I need to buy a bike, the A over here, 1,000, bicycle is not present, bike is present in the message, and it gets a score of 1/10. And that means now we have here these three sentences. I need to buy a bike, I have to buy a bike, and I have to buy a vase, in which the Euclidean distance without the IDF part before would have made no difference between B and A and B and C, because for each comparison, one word is different. Here, need and have is different, and there, bike and vase is different, and the rest is the same. So Euclidean distance without the IDF normalization would treat those two sentences A and C as having the same distance from B. But by taking IDF into account and by saying that that basically bike and bike and vase versus bike, that is a more that difference has more impact than the less frequent need and have difference. That really gets us to differentiating those sentences. So if we now apply Euclidean distance on those re-ranked scores, then B and B to A is smaller at 0.014 than B to C, which would have a Euclidean distance of 0.14. With tfidf, we have established a good way to represent text as a vector, and that is the standard way that is used. And that means we can apply distance measures such as Euclidean or cosine similarity, and we can apply K-nearest neighbors as we've seen it from the images before. The only problem that still arises, and that is a little bit different than the images, is that the vectors may be huge and we still cannot capture meaning. We cannot capture that bike and bicycle are similar to each other and should therefore not be treated in the same way as bike and vase, for example. Let's look first at the huge vectors. If we really do this for language over large corpus, then the vectors become really mighty. So everyday English covers about 10,000 words, but if we really total this up, then this can easily become 1 million different words. And that means that every message that we would be considering, even a short OK, would be represented as a vector with 1 million, or let's say 10,000 dimensions. Now, we could try to reduce this by going to trigrams. So instead of representing words, we could just have 3 consecutive letters, and that would reduce from the 1 million words, because 26 letters plus a space symbol means 27 to the power of 3 is nearly 20,000. So we could go from 1 million to 20,000, but if we limit ourselves to kind of everyday English, we would also be in that order of magnitude. And nonetheless, it would be that our simple message OK would be a vector in a 20,000 dimensional space where just one dimension is not 0. So that means everything fine. We can apply all of the techniques and principal component analysis and everything to these vectors, but in most cases they will be very sparsely populated, and that may create a problem. We could further address this by using the byte pair encoding that we have spoken about earlier, and that would further compress. But if you remember, we could compress the text of the ham and spam messages by, I think if I remember, 40%. The compressed version was about 40% of the non-compressed version. So that would mean we would maybe reduce our dimensions from 10,000s to 5,000. But still, it's not very, very compact. But be that as it may, there is a little bit we can do about reducing the amount of dimensions, but it will remain sparsely populated vectors. However, none of this compression and changes in representation of the dimensions can address our problem of the meaning of words. And that's where then a different approach came into play that is called word2vec. And the goal of this work that was created in 2013 was how to represent words as dense vectors, which captured the meaning of words. And in fact, the idea was that you could define beforehand how many dimensions you wanted these vectors to have, and you actually learn the vector representation that is capturing the semantic and meaning of the words. And essentially, this word2vec approach is a shallow 2-layer neural network that is trained to reconstruct the linguistic concept of a word. And the idea was that with these vectors, for words, we want to be able to do reasoning in space. So we want to be able to say that the distance from man to woman is the same as the distance from king to queen, or the distance from man to king is the same as from woman to queen. And this was published by Tomasz Mikolov, who was at Google at the time in 2013, so a little over 10 years ago. The paper is cited over 45,000 times, so it has a huge impact. And we just briefly capture the intuition behind what word2vec was trying to do. The key idea is that instead of counting occurrences between a word and its context, we represent words as models that predict the word from the context. So the idea was to take a word like bike, for example, and it would appear in our corpus that we're dealing with, for example, all wiki pages or all social media messages or any text that was ever written. And we take context into account. So we have a corpus given, and now we take our word and we have context. So these are n words before and after. Typically very short, just 2 words before, 2 words after, 5 words before, 5 words after. So what will we find with the word bike? We may find the words chain, tire, flat, cycling, and so on. These words might appear in the context, and you can see right away how this works, because the context for the word bike will be the same as the context for the word bicycle. And that is what we will ultimately exploit in our reasoning. We create positive training data by creating all of those example words that co-occur together with our target word in the context. And we create negative training samples by taking the target word and randomly picking any words from a whole corpus. And now we apply the simple neural network, so we can go back to the early lectures in week 2, 3, and 4, where we looked into gradient descent and logistic regression. And we can apply these techniques. So the authors of word2vec applied gradient descent on a simple, shallow, just 2 layers neural network to predict the word from its context. And a key idea was then, instead of using all of this context information from the original corpus, which is massive, which may have been gigabytes or even larger of training data. So instead, we're just using the weights of the network that was trained for this prediction task. So we say, rather than representing the context of a word directly, we take as a representation of that concept the model that is predicting that context well. And you can consider it like this if you remember this drawing where we, in week 3, explained how to basically turn a regression problem into a classification problem. We had positive examples, we had negative examples, we had a regression line that separates the two. That's our model. And a key idea of word2vec is that all of these massive amount of data, so let's imagine this is not just a handful of points like here, but these are maybe millions or billions of data points over here. So instead of representing our word by all of these billions of data points, we just represent it by the model that is separating the positive examples from the negative examples. And so the model is a very compact representation of an aspect of the word. And that is the basic idea behind word2vec. And at this website, you can explore such embeddings, and you can type in words and find similar words that were generated according to this method. Then the next step in 2018, this idea of word2vec was further expanded, where word2vec tries to build this model that predicts word from context, but it has center stage the word on its own in a static manner. That means bike will basically create such a context model, and bicycle will create another one, and they're similar, and vase will have a third one that is different from the other two, but that's it. It's static. It does not further consider the context of a word. And so the next step was to consider the context of a word, to not ignore what is written around the word that we want to classify in the semantic, or that we want to represent in the semantic way. And so from 2013 to 2018, it took another 5 years until this idea came about. And then in 2018, BERT was published, which essentially takes this word2vec idea to the next level, in that it creates transformers that map a sequence of words on the input side to a sequence of words on the output side, and it does so by repredicting words that were crossed out in the initial data. And by the way, just published in 2018, the paper has over 125,000 citations already now. And so BERT, the bidirectional encoder representation front transformers, was really the basis that set the stage for this notion of word embeddings, and that is ultimately the basis for ChatGPT and the likes. So take-home message, you should understand how to represent images and text as vectors. Once they're vectors, you should understand how you can apply Euclidean distance or cosine similarity and what their characteristics are, and why there's not one definite distance measure that is always the best. You should understand how to search with K-nearest neighbours and the principle of scalable architectures for these nearest neighbours. You should understand how to represent text with tfidf as a vector and what the key motivation for tfidf is. And you should have a basic idea of how to represent the meaning of words through the use of the models that allow the prediction task of the word from the context as it was coined in the word2vec approach in the beginning.